All right, so we're working our way through various applications of digital logic. We've figured out how to use the binary number system to store numbers and represent numbers with zeros and ones, or electronic signals. We found out how to make logic gates last time to make elementary operations such as and, or, exclusive or. And what we're doing today is building some of the next building blocks, the next level of abstraction. We're building memory elements. We're going to build counting elements, things that can count up in binary for us, and methods to do arithmetic, binary adding. And we'll start with memory and go from there. So memory, specifically a 1-bit memory, we're going to make with devices called flip-flops. And we can make them out of the elementary gates that we've already studied last time. So we can make them under NANDs and NORs. In the lab, you're going to make a data latch flip-flop out of NAND gates. And I'll show you something different this time, which is perhaps the simplest type of flip-flop, 1-bit memory. It's a RS, a reset set flip-flop. And we can make that with NAND gates as well. But just to mix it up, let's make it with NOR gates. So the basic setup is something like this. So we're going to have this abstract unit, which can be reset. In other words, Q will be set to 0, or set, Q will be set to 1. And it'll just await and keep whatever state it's in until you write something new to it. During that time, you can read the bit as many times as you'd like. And that's a reset set latch, or an RS latch. So let's find out how we actually build them using NOR gates. So this is the setup for a RS gate, an RS latch, or an RS flip-flop. So in this case, oops, I forgot the Q bar here. Remember, Q bar just means the opposite of Q. So if Q is high, Q bar will be low, and vice versa. It's made by these two NOR gates, not OR. Let's remind ourselves what a NOR gate is. We can construct the truth table. And it's a NOR gate means not OR. So we just take OR and we do the opposite. So OR is almost always true. The only way OR is not true is if both inputs are false. So we just flip that, and if both inputs are false, NOR will be true. And in all other cases, the NOR gate will be false. So let's try to analyze this. There is something weird going on here. The first NOR gate, the output of it is sent to the input of the second one. That's fine. But the output of that second one is then sent back into the input of the first one. So how in the world do we analyze this? We just do it systematically. So let's go into reset mode. Let's figure out how to analyze this. We're going to set the bit, the output, to 0. Let's see how we do that. We'll go R is equal to 1. So it's true that we're resetting. And S should be equal to 0. And we'll work through that. We'll connotate this by orange pixels here. I was going to say ink. So we have a 1 here and a 0 here. Now let's just look at our truth table here. If there ever is a 1 at any of the inputs of the NOR gate, the output, no matter what is at the other one, it's got to be 0. So there's Q is automatically set to 0. Okay, that's what we want. How about Q bar? Well, that is whatever S is putting out. But whatever it was a nanosecond before we set R and S to 1 and 0, it is now has this 0 clamped, this input is clamped to 0. Okay? Now, I don't know what the output was right before that. R could have been getting 0 or 1 at its other input. It doesn't matter. Because it has a single 1 there, no matter what, it's always going to be 0. So this other input is forced to 0. And therefore we have a 0, 0, and this will go to 0, 1 as we want. Fine, okay. Let's do another case. In green, we'll do reset equals 0, set equals 1. In other words, we're trying to set the output to a 1. We're just worrying about the setting, not the storing mode yet. Well, in this case, it's a very similar analysis. We have a 0 and a 1 here. And remember, anytime there's a 1, this thing is going to be 0. And there, that 0 will then feed back into this gate. 0, 0 will produce a 1. And we get our output. I should actually enumerate them here. So that Q, in this case, will go to 1. And then Q bar is whatever Q isn't. In this case, it'll be 0. In the other case, of course, we had Q goes to 0. Okay, so let's just say we don't want to write anything. We just want to use the memory and read from the memory whenever we need it. Well, in read mode, what we're going to do is we're going to say neither reset nor set. R is equal to S is equal to 0. Okay, so let's analyze this. If R and S are 0, maybe we can clean this up a bit. If R and S are 0, let's figure out what the output is going to do. Now this is the key. It depends on whatever the input was. So let's just say there's two cases. If we happen to be in the set stage, 1 and 0, well, here we're going to have a 1 being sent back down here. So we'll have 0, 1, and we know that goes to a 0. So now that goes to 0, 0 goes to 0, and we had 0, 0, that goes to 1. So if we set R and S equals 0 and Q is set to 1, it stays that way. How about the other way around? If we had Q was 0, and Q bar would be 1 in this case, if we had that, well, we have 1, 0 going here. It's going to stay at 0. And we have 0, 0 in the other one, and that's going to go to 1. So this is storage mode. Whenever we don't want to use it, we don't want to be setting data, we just flip S and R back down to 0. And it's just going to maintain whatever state it's in. And we can measure that a whole bunch of times. That can be sent to different places in our computer. And it's just in storage mode. There is a pitfall with these RS latches. What happens if we give it some nonsense? We say, I want S and R to be true. I want it to be 1 and 0 at the same time. I want it set and unset. Well, this thing probably will get fairly confused. Let's see what the output is. If we go R is equal to 1 and S is equal to 1, well, if there's any 1 in any input, it's automatically 0. And that's the same for both of them now. So the RS latch is neither true nor false. Not Q and Q are both equal to 0. So that's a flaw of the RS latch. Now, there are other types of latches we can use that get around this problem. This one's just a nice one to understand. One of them you're going to look at is the data latch in the lab. Let's have a quick look at that. So this is what the data latch circuit looks like. Note that there's not two inputs specifically for setting and resetting. There's just a single input, which is data in here, and that is what we're going to write. We have to somehow tell it whether or not it's in reading mode or storing mode. So in order to do that, we have this second gate here, this clock gate, and the way that this particular chip works is that if the clock is high, then we can pass data through. If it's low, it's just going to ignore it and hold on to its previous state. And that's basically because if we have a 0 into a NAND gate, the output is always true. And that puts this section here, which is basically like an SR latch, into storage mode. However, if the switch is high, rather the clock is high, it's just going to pass data through until the clock falls low again, in which case it's in storage mode again. So I show an example of how to wire one of these things up in a separate video, and I'll put a link to that in the description of this video, because sometimes putting this on a breadboard makes it make more sense, although it can be kind of messy because there's a lot of wires involved. Okay, there's one more type of flip-flop that I'd like to talk about. It's the JK flip-flop. I'm actually not sure why it's called the JK flip-flop. Should look that up. It's just kidding, I guess. I don't know. But let's see. So I'll put it in here. Okay. So here's our JK. This is just the abstract version of it. We won't have to build it from... It's very similar to a triggered or a gated SR latch, but we're just going to treat it as an abstract black box now. There's my D latch, and this is the JK flip-flop. So again, I have two inputs like the RS latch. I have a J and a K input. And by setting J or K to 1, while the other one is 0, I can set Q to 1 or 0. And these are usually edge triggered. So they're only going to listen when the clock input makes a transition. Right? So we had our clock here, and it for the data latch, and it passed information through all the time. This is an edge triggered circuit typically. And basically what that means is it has a normal clock input, but it's capacitively coupled. We remember this from our RC circuits and also from our high-pass filters analysis. And if I have an RC high-pass filter like this, what this thing is going to look like is it's going to get a big spike when you get the sudden change, and then it'll do this exponential decay like we're used to, and it'll spike the other way. So let's just take a diode. We'll put it one way or the other. Maybe we'll put it this way, and therefore block out the positive spike, and only on the falling edge is the clock open to copy out to the output. So same idea as the RS, but it has a feature. Now, if I set J and K simultaneously to true, it doesn't give you nonsense. It actually goes into a special mode, toggle mode. And this is actually quite useful. If my clock is going like this, low, high, low, high, what it's going to do in toggle mode, if we set J and K to be true, is the output, Q, is going to flip every time we get a falling edge. So it'll go up and down and up and down and so on. And this is a very interesting thing in itself, because what we've made is a frequency divider, right? Because if we're sending in like a 200 hertz square wave, what comes out of it is a 100 hertz square wave. We could feed it into another JK flip-flop in toggle mode, and it would be a 50 hertz and 25 hertz. So we can do frequency division this way. But it also has another very interesting application in terms of counting. So that brings us to our next topic, counting circuits. We've done memory, let's do counting. Okay, so how are we going to use this to count? Well, let's make a few of these. We'll make a few copies of them. Okay, and what I'm going to do is I'm going to put my input, my clock input as usual, into the input. And for all these, we'll put in toggle mode. We'll say J is equal to K is equal to high, 1, 5 volts, whatever it is, true, whatever we want to call it. Let's just call it 1 for now. J equals K equals 1. And so we're in toggle mode for all of these. What we're going to get here is we'll feed this to be the clock of the next one. And that would be the clock of the following one. This is a divide by 2, 4, 8 circuit, but this also will function as a counter. Let's see why. So first of all, let's just try to map out what we're going to get here. So there's my clock. Now that's also the input to the second one. So what we'll do is we'll put maybe a little light here, a light emitting diode, or a light bulb. Let's put a little indicator here. And we'll put one here too. And why not? We'll put one here as well. So what is the orange one going to look like? Well, if it's initially low, it's going to stay low until it sees a falling edge. It'll flip, 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 like that. That's what the output's going to look like. How about the red one? Well, it's triggered by the, the red one is triggered by the orange input, so it's going to look like this. Flip, flip, flip. And the blue one, well, that's triggered by the falling edge of the red one, so it'll do something like this. And that's what the outputs are going to look like. Now, let's look at the state of all the LEDs at all points in time. What we'll do is, why not just call this number 0, 1, 2, 3. So at this point, everything is 0. 0, 0, 0, 0. After one cycle, we have 0, 0, 0, 1 at that point. And then we have 0, 0, 1, 0. And then we have 0, 0, 1, 1. Every time we have a clock cycle, we get a new flip. 0, 1, 0, 0, all the way down. But this is exactly what happens when you're counting in binary. So if we're enumerating in binary, let's see, we have 4 bits here. Let's see what we're going to do. We might count up 1, 2, 3, 4, 5, ... And look at the state as we're counting up in binary. Well, 0 is just all zeros. 1 might look like this. And we see that when we're counting in binary, each row is kind of like a frequency division. You see that? 0, 1, 0, 1, 0, 1. That's our 2 to the 0. Our 2 to the 1 column, 0, 0, 1, 1, 0, 0, 1, 1. Our 2 to the 2 column, 4 zeros, 4 ones, and it'll be 8 zeros until we get all the way down, ... to 14, 15, and what happens when we get to 16? That'll be interesting. But 14 in binary will look like 8 plus 4 plus 2 plus 0, 1, 1, 1, 1, that's 15. And then when everything's high again, when we flip it, the flip is going to go to each one of them, and it's just going to toggle down, and what we'll actually get is 0 again. So this will allow us to count from 0 to 15. If we're not including the clock, it's a 3-bit counter, but it will count from 0 to 8. Okay, it's nice to do in theory. Let's actually build one. So I'm going to take 2 dual JK flip-flops, the JK112 variety of flip-flops, and what we're going to do is just build one of these things. We'll build a 4-bit. So a 4-bit binary counter, and see what that looks like. Okay, so here is a 4-bit counter fed by 2 JK flip-flops, and they're both in toggle mode. So as discussed, the output Q of each one goes into the clock of the next one, and the readout is given by these LEDs here. The clock itself, instead of manually toggling it, is just fed by this Arduino, or Teensyduino actually, at 4 Hertz from one of these pins, and I can pass it through by flipping the switch. So let's do that. Let's start counting. And there we go. So it's counting up in binary. This is the 1, 2, 4, and 8 bits. And we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, back to 0. A 4-bit counter. In fact, it's a 5-bit counter if you count the clock, but let's just consider this as a 4-bit counter. And this could be an event counter. Say this is coming from particle detections and you want to count for a given amount of time. You disable it at some point, and we see that we got 0, 1, 1, 1 events in this case, which corresponds to 14. All right. Okay, so that's great. With our knowledge of performing logic and storing numbers with binary, we know how to make memory chips and we know how to count. There's one last thing we want to do today, and that's binary addition. So let's go way back to like grade 2 or grade 3, and remember what addition was. So let's do some addition. Okay, so Mrs. Appleby wanted us to add 74 plus 22, and how she told us to do it. Always look at each column independently. 4 plus 2, well, that's 6. 7 plus 2, well, that's 9. 96. Awesome. But then we ran into a bit of trouble when we had to do 74 plus, 28. For now, we had 4 plus 8, that's 12. That doesn't fit here. But that's okay, because 12 is just 10 plus 2. So we just added a 2 down here, and a 1 to the tens column. That's that extra 10 we got to deal with. And we get 1 plus 7 plus 2, and that is 10. So again, we just put the corresponding column there, and we get 102 if we did our math right. So we want to mimic the same thing with binary. Binary is the exact same thing. Let's just do the same analysis. So we have, I don't know, what is this, binary for 5? Well, let's just see what it is. 1, 0, 1 plus 1, 1, 1. Well, 1 plus 1 is 2, 1, 0 in binary. So we have a 0 here. We carry the next column, the 2's column, I guess. Previously it was a tens column in decimal. And now we have again 1 plus 0 plus 1, which is 2 again. So that's 1, 0. And now we have 1 plus 1 plus 1, which is 3. in binary, that's 1, 1. So this translates to 5 plus, what is this? 4 plus 2 plus 1, so that's 7, is equal to 8 plus 2 plus 0 plus 0, that's 12. And we've done some advanced math. So we want a circuit that does this. Let's try to figure out how to make a circuit which is going to do this addition for us. We'll concentrate first on a row by row picture. Let's just look at the algorithm of addition of binary numbers. So if we have two numbers, A and B, two binary numbers, two 1-bit binary numbers we want to add, A and B, well, we'll have our sum, which is A plus B. And if A is 0 and B is 0, the sum will be 0. If A is 0 and B is 1, sum will be 1. If A is 1 and B is 0, well, the sum will be 1 again. And if A is 1 and B is 1, well, in this case, the sum will be 2, binary for 1, 0. So we need that extra digit. To add two 1-digit numbers, you can verify this with decimal, you need 2 placeholders. How many do we need for a 2-digit addition? Like 99 plus 99, that's as big as it's going to get. 198, we need 3 placeholders. So in general, we need 3 bits to store the addition of 2. We need 2 bits to store the addition of two 1-bit numbers. We need n plus 1 bits to store the addition of two n-bit numbers. Okay, so we need an extra column here, a carry. And that's almost always going to be 0 unless we've carried over that additional bit. Okay, so this is the truth table we need to make, and it's 2 devices, right? We need 2 outputs, a sum and a carry. But let's look at this. We might recognize these truth tables already. The sum is nothing but an exclusive OR. And the carry, well, that's an AND gate. We know this already. So let's just wire an exclusive OR and a carry like this, and a AND gate like this, and we should make a 1-column part of an addition unit. Okay, here's A and B, and we'll just go into an exclusive OR gate, and that's the sum. We'll tap it out to the AND gate that we put in here, and that's the carry. And this is a circuit which performs the algorithm of addition. It just adds two 1-bit numbers. We're going to put it in a black box, as we do, and call this a binary half adder. That's a binary half adder. Okay, great. It's not quite a full adder because we need to maybe have multiple columns and arrange them in the right way. But we can basically look at this algorithm of addition and find out how to deal with the addition. What do I mean by that? Well, this will always work actually for this first column. That's fine. This first column in yellow here, this is always going to work for that. But what about the next column when I had an additional input? I actually need 3 inputs. I need the carry from the last operation plus whatever 2 numbers are in the columns that I'm adding now in that 2's column or 4's column or 8's column in binary addition. So let's just make a 3 input device and think about what we need to do. Because really what we're doing is we're adding everything up. We're adding the sum, the carry, and we're adding A plus B plus the carry and storing it in 2 numbers. So let's have a look at that. So let's set this up. We're trying to add the nth digit of A. We're looking at the nth column here. Just to be clear what we're doing, maybe A is equal to 0 in this case, or it's equal to n is equal to 1, so the nth column, or 2, or there could be a much bigger number. So in general, when we're doing the nth column here in this addition, we want to find out what the answer is. We're going to need 3 inputs, the 2 numbers in question, and whatever the carry was from the last column. Okay? And those are going to go in, let's just apply our number. Those are going to go into our binary half adders. That's going to have a carry and a sum. But what did we do? Well, we added our sum, or we added our carry with our sum of a plus b. That's what we were doing literally before when we're adding these up. Look at this column here, 1 plus 1 plus 1. So let's just stick that into another binary half adder. And that itself will have a sum and a carry. So we'll keep whatever the sum is, and that's going to be the result that goes into the column of the lowest digit, right? So look at this, in this case here, the sum was 1 plus 1 plus 1. Okay, so the first 1 plus 1 gave us 1, 0, and we had to add one more, which gave us 1, 1. So either way, the sum is just going to be whatever comes out of the sum of a plus b plus c here. But how do we deal with the carry? So under what circumstances is it 0? Sum will only be 0, like we actually look at what we're doing here. The carry will only be 0 if the sum of these is 0 or 1. If it's in other words, only one of these things can be non-zero. So in that case, the carry will be 0 between these two. Or if one of these is 1 and this is 1, then the carry, and this is 0 rather, the carry will be 0 here. So we can encapsulate that with an OR gate. And that's the sum here. So this will allow us to handle the overflow problem of 1 plus 1 plus 1, in which case the sum is 3, 1 plus 1. If we have 1 plus 1 plus 0, or 1 plus 0 plus 1, or 0 plus 1 plus 1, let you verify all those, we're going to get a sum of 2. So the carry will be 0, but the carry will be 1 from one of these two operations, but the sum will be 0. Okay, so that exhausts everything. And this is, we can put into another black box or a purple box here, and we will call it a binary full adder. So now this binary full adder, what's the difference? The only difference is it handles the case that we also had an incoming carry from the last operation. And this is important because it allows us to make n-digit additions. So let's make a circuit which adds up two 3-bit numbers. How we're going to wire that up? It'll be something like this. So we'll have our first 3-bit number, 0 through 7. For example, 5 would be A0 equals 1, A1 equals 0, A2 equals 2. But let's just leave it 1, but let's just leave it abstract for now. So we have our second 3-bit number, B0, B1, B2. Again, these can be either 0 or 1, and we can make any number, any 3-bit number this way. And let's wire them into our adder circuits. So how are we going to do it? Well, performing, again, the operation, let's just mimic the algorithm that we were doing. We're just going to look at a column by column output. So A0 and B0 will go into our first binary full adder. And that's going to have a carry and a sum as before. So let's just put it this way. And this will be the first digit that we get. Well, we have to use that carry for the next one. So let's do that. And we're going to put this into our binary full adder. And that will be extracted to give us our next digit. So this is the 2 to the 1 component of our addition. All right, so we'll wire another one up. Don't forget that we're typically not wiring all these up by hand. These things can be etched onto a printed circuit board and made very, very small, and attached to a printed circuit board rather. So we're going to put another binary full adder, and we're going to get the result of that column. In our previous example, that would be this one here. So that will go to S2, our 2 to the 2 component, and we have our carry. But now that carry is just going to be the final digit of our addition, because as we said, we need 4 bits to store the result of a 2 3-bit numbers, the addition of 2 3-bit numbers, that is. And this is how we could make a n-bit addition circuit. Just with electricity now, where are we at? With electricity, we can store numbers and represent them. We can do logic, build basic gates. We have memory. We can remember things in some sense. We can count, and we can do math. And this is kind of the next layer that we're building up of computation. After that, we're going to look at ways of measuring, going from this analog world that we've been living in the first half of the course to the new digital world that we're talking about now, with analog to digital and digital to analog computers. But that will be next time.